And we can go on to the next presentation, which is Emeka Chisoke.
Yes, sir.
Chiyoke,
Chijoke,
from
yes.
Warsaw University of Technology, talking about energy optimal electric rotorcraft missions. Emeka,
Yes.
so it's yours.
All right. Hello, everyone. My name is Emeka Chijoke, and I'm a doctoral researcher at Warsaw University of Technology, Faculty of Power and Aeronautical Engineering. And I'm really glad to be here today to present our work on accessing the impact of actuator and rotor dynamics on energy optimal electric rotorcraft missions. This study arises from the research study that we have performed on optimizing the energy consumption of an electric-powered unmanned helicopter. During a drone competition, my science club team and I flew an electric UAV over a simulated chemical-contaminated airport. And the mission was to release light beacons to mark the danger zone for firefighters. And halfway through, we replaced the battery. Not because of a failure, but because we knew the power wouldn't last long for the whole mission. And that moment made me realize how crucial energy optimization is in UAV operations. So we have achieved energy optimal. And we are asking the question, what if we implement actuator and rotor dynamics on this energy optimal that we have achieved? What will be the influence? So I hope I will do justice to explaining that to you. And this will be the structure of my presentation. So I will lead you through the introduction and motivation of the work, the research gap that we have found through our literature review, and the objectives of this study. And I will show you the methodology that we have used to perform this work, and then the results and conclusion. And the results might be shocking. All right, so starting with the introduction. Electric rotorcraft, especially helicopters, have a serious limitation: endurance. The more they spend time climbing, hovering, changing direction, the more energy they consume. And once the battery drains, the mission ends, whether the job is done or not. And unlike fixed-wing aircraft that can glide, helicopters must power their rotors consistently, making them energy hungry and less efficient. So the challenge isn't just battery size, it is how efficiently the UAV uses energy during flight. So now we goes to what is the essence of this work that we're doing? What is the motivation? Electric rotorcraft are increasingly used in applications such as data collection, infrastructure inspection, search and rescue mission, and these operations require reliable estimates of endurance and energy consumption. So you want to make sure, if you're working in industries that uses these fleets, for example, emergency services, delivery industries, you need to make sure that your fleets are well planned. The flight paths are well planned. You have enough energy capacity to carry out the activities that you're performing. So let's say, for instance, you're working in emergency services and you have to transfer a heart to a patient in a hospital needing a heart transport, and you don't have efficient performance of your fleet. Let's say that along the way you have a malfunction. The battery is not.
You don't have enough battery capacity to transport the donor heart to the hospital.
Now we have a problem. The patient in the hospital, we don't know if he's going to live or not. So there is a need to make sure that your fleets are very well planned. You have efficient enough energy to carry out the activities you plan it to perform. Now, what is the research gap that we have obtained from literature review? Most of the optimization studies do not implement actuator models, rotor dynamics models, and they are losing out from the energy they can achieve. So it is very important to make sure that these actuator models, the optimization system that you are having, you are making sure that you're achieving realistic energy optimization. So So these studies did not implement actuator limits. They do not implement rotor dynamics in order to see the benefits that they can achieve. Because in real life, these UAV systems do perform realistic inertial motion. So you have to apply the delays in the transient stages of the flight to see how the actuator model performs. So the objective of our study, which is the implementation of the actuator model, is to compare our ideal energy optimal case against these constrained models that we have applied. And then we want to quantify how this actuator model influences our total energy consumption, the trajectory, traffic, and then the power demand. All right, so the methodology that we have adopted is a parametric search, iterative search of the parameters that leads to energy optimal. So first, we want to specify our mission. So we want to do a hover, ascent, cruise, and descent. So this is our first step. And then we are simulating the model. We are using a FLIGHTLAB plus the MATLAB Simulink for parametric energy search. So the FLIGHTLAB incorporates the 60 degree of freedom rigid body, nonlinear rigid body. And the MATLAB helps to supervise the simulation. And so the next is that we are applying the dynamic model to see the influence it has on the optimal energy. And one more thing is that the stages of the achieving the energy savings from our simulation is first. We are simulating the baseline. So we have a baseline simulation which is 1,000 RPM with a fixed flight path. And next stage is to simulate individually the rotor speed to see the influence it has on the total energy. And the third stage is to individually simulate the flight path, changing the parameters to see the influence it has. And the fourth stage is to implement these two strategies together to see the influence. And that is a simultaneous play with the parameters of the flight path and rotor speed to see the influence on the total energy obtained. And the last stage is to compare our results, how this actuator model influence our the trajectory tracking, the power demand, and emission consumption. And this is the simulation setup that we have. So this is our mission profile. We started So we say we want to do a hover, ascent, cruise, and descent phase. And this mission has a duration. So hover takes 40 seconds, and the ascent takes 30 seconds, and the cruise takes 70 seconds, and the descent takes 60 seconds. And the whole mission takes 200 seconds. If you observe, we have a long duration in the cruise phase, and that would explain the dominance of this phase in the total energy consumption. And we are attaining the altitude. The hover is 34 feet, and we climb to 80 feet maximum, and then return back to the descent phase from when we started, which is 34 feet. And the simulation requirements already explained, but to elaborate more. So it is a MATLAB Simulink that we are incorporating with FLIGHTLAB, non-linear degree of freedom. And in this system, we are using a powertrain experimental result that we have obtained to see the power consumption of this experimental result that we have performed. And then it was implemented into MATLAB as a lookup table, so that when we are making simulation, changing rotor speed parameters and flight path, this action we take the power equivalent and then transform it to the energy that we need. So it will be an integration of the power consumption that we have obtained. Okay, and you will want to load the configuration of the UAV that we're using. So this is an action model developed in our department, and it means autonomous, reconfigurable compound helicopter for education and research. So it has the mass of this actuator that we are using for this study is 7.3 kilograms. The main rotor diameter is 1.78 meters, and the tail rotor is 0.158 meters. And when as I have already explained, we have a baseline rotor speed set for further optimization purposes, and that is 1,000 RPM. And when we are doing the individual rotor speed optimization, we have range between 850 to 1,000 RPM rotor speed. So this is because we want to simulate if we are doing a hover, the hover will take for example, 850 RPM. If we are climbing, we can take 900 RPM for the ascending series. And with this process, we will see the influence this changing of the parameters has on our energy optimum. Okay, so just to say more about this actuator rotor dynamics that we have implemented. So this is a rotor dynamic constraint. So we are limiting the rotor speed to replicate real life dynamics. So we are limiting the rotor speed to 10 RPM per second. And we are using the first order rotor response, okay, to replicate a real life dynamics of the UAV. And this also a rate limiter was applied on the velocity, on the speed, and on the altitude, just to simulate real life, just to simulate the smooth path of our flight, and also to minimize the spikes around the transient series. And this is the energy model. I have already explained that. So we are using a MATLAB lookup tool to implement our power model, and then we are integrating that power to get our energy consumption. Okay, and coming to the results. So this is the flight profile. If you can see, this is between our actuator model and so I will use the term ideal and realistic model. So the first one is the realistic model, the black curve, and the green one is the ideal model. You can see that both cases follow the trajectory, no huge discrepancies. And the dynamics introduces some delays, but these delays are not really huge. Okay, and this is the rotor response. Okay, and you can see that the way the ideal cases is flowing. This is the power, the rotor speed. So you can see how it is instantaneously flowing. But when we apply the actuator model, the curve goes smoothly. Okay, and this is the influence on the total energy. So there's no huge impact of this rotor dynamics, and we have just the phase energy difference remains only below 1%, and the total mission energy differs only 0.2%. So no huge differences. So in conclusions, we say, all right. So our energy optimum, when we are doing the simulation, we achieve 25% energy savings, And now, when we apply the actuator model, there's no huge discrepancies. It's only 0.2% changes. And the dynamics influence the transient visibility. So it's only the transit stages that this actuator model influences. And then the future work, we want to investigate the more aggressiveness maneuvers of this UAV and to see how the actuator models will work. Okay, that will be all. Thank you very much for your attention.
Lucas.
Thank you for your presentation. My interest aims at the use of translational lift, because what I would expect, maybe I didn't orient myself fast enough, but was a translational lift included? Because the cruise phase, I would expect the power consumption to drop off quite significantly depending on the translational speed.
No, so because of the long duration of the cruise phase, it has a dominant influence on the total energy consumption. So what we did was to specify different rotor speeds along these stages. It's not like a one static rotor speed. So we are, let's say for example, on the hover, we are taking 850 RPM, and on the ascent, we are doing just a little bit of the discrepancy of the rotor speed to see the influence it has on the total energy consumption. So it's not that we have doing the any rotor speed optimization that we have a constant rotor speed. We are switching between phases to see the total.
Yeah, you always take the optimal RPM actually.
Yes. So
yes, but I was aiming at translational lift. That means that when helicopter is like translates with movement, so then the airflow through the rotor changes, and usually the power consumption drops a bit. And quite significantly.
If I understand your question, we simulated only a typical flight path of a UAV. So we did not incorporate a drastic movement of this UAV. So it's a typical hover, ascent, cruise, and descent phase.
So the cruise is relatively slow, I should say. The cruise speed.
Based on this, yeah. Okay. So I will have to show you the rotor speed that we have used on this rotor speed on this cruise stages, so to show you the influence. But the influence of what we have studied is that because of the fact that the cruise takes longer than the rest of the phases, it has a dominant effect on the total energy consumption.
The second question?
I'm not sure. My question is very similar to Lucas, because I want to ask you, you write on the previous slide that you optimize the efficiency of the flight, but
Which one? The slide?
almost the last one, just before the thank you. No,
This one?
Next one. Energy optimization.
25%? Is that the one?
No, I simply want to ask you about this optimization. What do you optimize? Because you get a different result if you optimize the range or the time of flight, or if I understand good, you you minimize the energy used to make the constant parameter mission, yes?
So this is a parametric search of the energy consumption. So what we're doing is to simulate the strategy is to see the influence of the rotor speed and trajectory path parameters. Now, to explain more, what is the trajectory parameters? Is the altitude, the velocity, and the climb rate and descent rate. So we are
trajectory parameters.
Yeah, so we are
and also use some kind of electric rotorcraft, and I see that, for example, the speed of flight has very big influence for the efficiency of the flight. And
That's correct.
your speed on the cruise stage is constant. Yes, we do not check different speed on the phase of cruise.
Well, if you want to see the influence of the speed, you need to see the influence by tweaking the parameters of the velocity, the altitude, and the climb rate and descent rate. So these are the parameters that we tweak and manipulate alongside with the rotor speed. So this is a combined simultaneous parameter tweaking to see how these parameters changes will influence our total energy savings.
Okay, thank you. I would propose to have further questions in the coffee break or in the lunch break.
Sure, I will love to answer.
Thank you again.
Thank you very much.
Thank you.